Come, let us talk about graph traversal. Graph traversal, we need to talk about the basic why we need to traverse a graph. Then we talk about breadth first traversal. In breadth first traversal, we need to see the algorithm, example, and implementation. Depth first traversal, how do we traverse in the depth? And some traversal applications, which is very, very important, and review questions. Now, introduction, you remember in tree we traverse in order, pre-order and post-order. And exactly when we look at a free tree is basically a connected undirected graph. So in a free tree, you understand that edge is actually vertex, and an example of a free tree is like this. You have some vertices and there is a connection. So when we consider a forest is an acyclic directed or undirected graph containing of two or more trees, generally. And the tree actually in a directed forest are rooted trees, and the tree is an undirected forest are free trees. So free trees and normally trees, you can understand tree has a single root, but if you have a free tree you have more than one root. So considering that, to traverse in a graph is to systematically visit, and you need to process each node in the graph exactly once. You remember that means you have a vertices, you are actually traveling in the graph means you go to each vertex and do some work. So there are two common graph traversal algorithm we generally have, and application to both directed and undirected graph. One is called breadth first traversal. That means I'm going across the breadth of the graph. Or it can be depth first traversal. That means I go deep first and then come up. So I can have two types of traversal. One is called pre-order depth first or post-order depth first. Since some graph algorithms do not require all vertex of a graph to be visited, so we will define both BFS and DFS such that breadth first and depth first, such that it's possible for the algorithm starting from any vertex will not visit all vertex if the traverse graph is disconnected. So take a look at here what happens in this DFS and BFS traversal of a graph. It is not unique. A traversal of a graph is like this. Depth first, you can understand that in breadth first traversal, we start with the first vertex and we try to cover across all vertices across the breadth. So how do we do that? In this method, after visiting a vertex V, we must visit all its adjacent vertex. So the concept is in breadth first traversal, you visit actually adjacent vertices. And then before going down to each next level, visit the vertices that are adjacent to W1, then visit the vertices that are adjacent to W2 and W3 and so on. So this algorithm works with finding adjacent vertex. So the method can be implemented using a queue. Why? Because generally I'm keeping the adjacent vertex in the queue and I take each adjacent vertex and then go across the vertices which are adjacent to that vertex. So a Boolean array is used, you see, in to ensure that a vertex is, actually visited only once. So what you do first, look at the algorithm, enqueue the starting vertex. That means you put the starting vertex in the queue, and then what you do, you are looping how go as long as the queue is not empty. So take out the vertex dq v from the queue and then visit v, and after that enqueue the vertices adjacent to V that were never, encountered, you never visited. So, a BFS traversal of a graph ultimately result in a BFS means breadth first. It is actually resulting in a breadth first tree or in a forest of such tree. So, the concept of breadth first traversal actually is adjacent vertex, visit through adjacent vertex, and you use actually Q to implement this traversal technique. Look at an example here. I'm going to actually have this graph, I'm going to traverse using breadth first traversal technique, and my starting is the A. So what I have in the Q, adjacent vertex is actually B and D, So when I put that A, and then I actually have it in the Q, and then my next is coming B and D, and after B you can see the adjacent of B is coming into E, and then C is coming, you see. Why? Because B adjacent is E and C, and then D is coming the G, and G then your F. Why? Because C is adjacent to F, and then H is coming because the adjacent of H, adjacent of G. So you are maintaining a queue in order to traverse the graph in breadth first traversal technique. And ultimately in BFS tree looks like this. You start and then you can actually have this traversal producing a tree. So this is actually a implementation. You are actually looping and you are actually NQ and DQ, the general concept that we discussed. So analysis of the breadth first, you see for a graph G where you have the vertex and H, and N is the absolute number of vertex, M is the absolute value of H. So when adjacency list is used, the complexity is of the order of M plus N, and adjacency matrix is of the order of N square. Now depth first traversal happens differently. A depth first traversal is starting at a vertex V. When you start with the first vertex, then some neighbor W of that V, you need to look at the neighbor vertex, and then some neighbors of W that actually covers all aspects of the tree. So what you have to do, you start with the vertex and then go into the neighbor and keep going. So must keep track of vertices directly, directly attached to the neighboring vertex, and also vertices which is already visited, to avoid actually cycles. You really have to avoid cycles when you are doing depth first traversal. Now the method can be implemented using recursion or iteration, because you are actually recursively, and the iterative, what happens, the iterative preorder depth first traversal algorithm is this. So what you do, you can use you are using actually stack. So you are pushing the starting vertex into the stack. So stack means, you understand, last in first out, and then you are looping. When the stack is not empty, pop the vertex of the stack and visit, and after that if V is not already visited, visit it, and then push vertices adjacent to V, and what you do, you not visit it onto the stack, and then keep doing through the stack. So what happens, you are actually traveling again depth first. Because why? Because I'm not taking care of all adjacent, I'm taking care of one adjacent and then take the next adjacent and so on. So it's basically depth first traversal technique. And take a look at this example, depth first traversal. I have a graph, I want to start, and I need a stack now. It's not a queue because it is actually depth first traversal. So what you do, you push A first into the stack, order of the traversal A, and then you understand that what comes into A is the adjacent. When you go to B, then B, then you go to C because you are going to depth first, and you go to F. Fine. After F, you understand that you come into what next value you come into, because you are actually, when you visit, you actually pop also. So stack is getting empty by the time you get to F, and then your C has no other, C already visited. So take a look, going back to B, is there any adjacent? Yes, E, so come into E first because you finished, so you come here E, and then after E, you go into the next adjacent is G, because from E to G, and then G to D, but you understand that you have to avoid cycle, so you come into actually G to H, and then finally I. So the traversal actually is the depth. You can understand it's not by breadth, because you are actually covering the depth of each cycle. So this algorithm works very nice in depth first traversal, and we will actually revisit the code while we will be implementing in C language. These are some of the recursive preorder depth first traversal tracing, how you do it, and you are actually pushing into the stack. So what happens, you are actually visiting the nodes according to your pushing into the stack, and you can see that what happens when you visit one by one, and go into the, and you are actually push into the stack, pop from the stack, and so on. So this technique actually we'll be discussing also in our programming while we experiment it. This is also recursive approach of implementing the pre-order depth first traversal. So the analysis of depth first traversal is same as with breadth first traversal, because the complexity is same if you are using adjacency list of the order of m plus n. Otherwise, it is adjacency matrix is square. All right, so these are actually applications which we discuss also, and the summary is very important, how we actually traverse the graph, and I will actually discuss a little bit more into programming while we do this. And these are kind of strongly connected component, SCC as we said. You can have subgraphs, digraphs connected into smaller components, and I can skip this part of it. So finally, I'm actually almost coming into the end of our discussion, that age classification using sometimes DFS, and how we are actually classifying different ages, and these are different applications of depth first traversal. I will skip, and we discuss more into computing, and is also a classification using DFS, so we skip this part. These are some of the review questions. Generally happens to given a graph and you consider the depth first traversal, then you write down the nodes the way you are traveling into the graph. With this, so I stop here, and we actually also do hands-on programming with a graph data structure.